Section 7.4, Equations with Rational Expressions. Alright, in the previous two sections we looked at rational expressions, okay, adding and subtracting the fractions that have these polynomials in them. Now we're going to have equations, so we throw an equal sign into the problem, and how this is going to affect the problem is that our answers aren't going to be fractions. We're trying to solve an equation, so we're trying to find the one x value that is going to make an equation like this be true. So 2 over what number, if you then subtract 3/2 from it, is going to equal 7 divided by 2 times that same number we find, plus 3. So these problems we're not done until we get x equals some number, or in some of these cases x equals 2 possible numbers, depending on what type of equation it is. First thing we have to do is to determine the domain. What x values can we plug into these rational equations? If you remember from, I believe it was 7.1, when we were finding a domain, we're looking at, what x values can we plug in based on the restriction we can't have 0 in the denominator. So we look at each expression's domain individually, each fraction, and then to write the overall domain of the equation, we combine all of those domains into one bigger domain. So our first example, 2 over x minus 3/2 equals 7 over 2x plus 3. We have to look at all of our domains, all of our denominators, and determine which x values can we not have. Well, in this first fraction, 2 over x, we can't have a denominator of 0, and since the entire denominator is just x, well, we have the restriction that x can't be 0. The second fraction, then, 3/2, we don't even have a variable in that denominator. So there aren't going to be any restrictions based on the 3/2 fraction. Okay. But then the other fraction, 7 over 2x plus 3, okay, well that is going to have a restriction in that whatever x value would make 2x plus 3 equal 0, we cannot have that. So then solving that for x, add or subtract 3 from both sides, we get 2x cannot be equal to negative 3. Then dividing on both sides by 2, we get that x cannot equal a negative 3/2. Okay. So at that point then we want to combine the three domains that we found and write it as one overall domain. So in combining the domains, we get the set of all x values as long as x does not equal a negative 3/2 or 0. Okay, those were the two x values we found we could not have in that fraction and in that fraction. So we just combine it into one bigger set of x values we cannot take for our domain. Alright? So that's how we have to find the domain in all of these equations, all of these rational equations, look at all of our fractions and see what x values are not going to be okay to take. So looking at our next example, looking at our denominators, right here we can see x, we can't let x be 3, because 3 minus 3 would give us 0. We can't also, from this fraction, we can't let x be negative 3, because negative 3 plus 3 would give us 0 here. But then over here we're not sure, maybe initially, what x values will give us 0 from this denominator. So if you remember with these, we have to factor, and then that will make it easier for us to see what x values would make this denominator equal 0. So we want to factor that, and it actually is a specific kind of expression we can factor. This is a difference of squares. Okay. So difference of squares always factor into x plus 3, x minus 3, something that has two factors that are identical except for their signs. One's addition, one's subtraction. X times x gives us x squared, the 3 times negative 3 gives us the negative 9, and if you were to FOIL it out, the middle terms would cancel. So it would just get us the x squared minus 9. So finding the domain based off of that, we see the same two x values are going to be restrictions here. what x values are going to give us zeros in those two factored parentheses. Well, again, this tells us x cannot equal -3, or from that parenthesis, x can't be +3. All right. And if you had done these first, well, x minus 3, if we had said, well, that can't be 0, that already would have told us from that fraction we couldn't have x equals +3. And then looking at the second fraction here, x plus 3, we weren't allowed to let equal to 0, while subtracting 3 from both sides there also would have told us that x can't be -3. Okay? So the restrictions, because of these two fractions, end up being the same two restrictions on this fraction. So we really don't have to combine anything extra. It's just the fact that we can't have a 3 or a -3. Okay, because that's going to give us issues here, here, and both of them in here. So if you think about it as combining them, we're just going to have those same two x values. So our domain is going to be all x values as long as x does not equal -3 and +3. Okay. Alright, so that's finding a domain of an expression or of an equation. The reason why that's important is because we could go through and solve these equations and find an x value as our answer, or maybe two x values. Again, we're going to have some equations that will have two. But if that x value is not part of the domain, once you find it, then we don't accept that as a solution. Our only solutions are going to be the x values that we can potentially plug into these fractions. And it needs to be an x value that we could plug in, so we do get something on the left-hand side that equals the same exact value on the right-hand side. So if we can't plug it in, because it's going to give us a 0 in the denominator, then really it's not a solution. So that's why we learn how to find the domains first. Now we're actually going to solve some equations. And to do that, let's recall how we can handle solving equations when we're involving fractions. We have a little trick where we can cancel out our fractions right away, and then we're only dealing with whole numbers rather than fractions. So, first example, we have solving the equation 1/3 x minus 1/2 equals 3/5 x plus 5. The little trick that we can do to clear our fractions is to multiply by the LCD of all of our fractions, the lowest common denominator. Okay. So our lowest common denominator, in this case, we have 3, 2, and 5 are our three denominators. We're trying to find the smallest number they all will go into. It's going to be 30. Okay, 2 and 3 don't go into 5 or 10. They don't both go into 15. They don't both go into 20. Neither go into 25. 30 is going to be the first number that all three of these can be multiplied into. Okay, so our lowest common denominator would be 30, and we're going to multiply on both sides of the equation in order to clear our fractions. Okay. So I think how you'll see it written, at least in my math lab, we put a parenthesis around the whole problem and write times 30. Okay, which is another way of saying we have to distribute that 30 to every single term inside of the in this equation. So doing that, if we multiply 30 times 1/3 x, really what's going to end up happening, I mean, you could think of this if you want as 30 over 1. We're really just going to be multiplying 30 times the numerators and 1 times the denominators, which will just keep the denominators the same. So 30 times 1/3 x is going to give us 30 over 3x minus 30 times the 1/2 is going to give us 30 over 2. 30 times 3/5 x is going to give us 90 over 5x plus, and then the last part, 30 times 2, is just going to give us 60. Okay. When it's not a fraction, then we don't have to worry about it. So then, this doesn't necessarily show why that was even useful. Taking it one step further and reducing your fractions, you will now have all whole numbers. 30 divided by 3 gives us 10. So here we have 10x. 30 divided by 2 gives us 15. So here we have 15. Equals 90 divided by 5 gives us 18. So we have an 18x. And then the plus 60 on the end. Now we have a nice equation, a linear equation that's just with whole number coefficients. Much easier to solve. We'll take some of these next problems out further, but I just wanted to at least remind you of the trick, how we can get rid of fractions. Okay. And the next, all the rest of the examples we'll look through, we'll finish the problem. So we're going to get plenty of practice of doing that. So now let's try to deal with this when we have a rational equation. Those equations had fractions and had a variable we would have to solve for, x. However, they didn't have the same kind of fractions we've been looking at here now. Okay, like the equations we just looked at above that we found the domains for. Those kind of equations, we want to follow the same idea. We want to look at our expressions. Okay, so our next example, 2 over x minus 3/2 equals 7 over 2x. Okay. We want to determine what our lowest common denominator is and multiply that in order to cancel out our fractions. And so we're still going to follow that same idea that we did with the regular fractions. So still want to multiply by our LCD. Which in this case, our LCD is, well, we have x, we have a factor of a 2, and we have a 2x, or 2 times x. So going back to 7.3, where we have to find our lowest common denominators of these, our lowest common denominator should be 2x. Okay. These both have an x and a 2. This has a 2 and an x. We want to kind of combine them to make those lists all match, which in this case will be 2x. So let's take our original expression and multiply everything by 2x. So I'm going to rewrite the original expression here. We have 2 over x minus 3/2. Leave some space to multiply things in here. And then equals 7 over 2x. Alright, so there's our original problem. But remember, we're going to multiply everything by 2x. So 2x times that, 2x times that term, and then 2x times that term. Okay. Alright, to make this easier on yourself, really we can just look at all these as putting them over 1. And then in each case where we're multiplying, we can look diagonally to cancel out common factors. So in this case, we have an x up top here and an x down here. Those are going to cancel. Over here, we have the 2 and the 2 up top and down below. Those are going to cancel. And over here, the whole 2x and the whole 2x will cancel. So you see in each case, the denominators cancel with something that was up top that you were multiplying by. This again gets rid of our fractions, and now all we are dealing with is the whole numbers. Okay. So we have ourselves 2 times 2, so we have ourselves a 4 here, over 1 times 1, which is just going to be a 1 down below. So again, that gets rid of our fractions. Minus, well, those canceled out, but we still have a 3 times an x. So 3x equals, on the right hand side, the 2x is completely canceled. All we're left with is the 7 up top. 7 over 1, which would just still be a 7. Alright, so if you kind of forgot that you could do that, a little note here, when you have common factors, they'll reduce. You can reduce them diagonally like we just did. But you don't want to do that when you're adding and subtracting, so that only works when multiplying. Okay? I think that's what we looked at in 7.1. Alright, so now we have to solve this equation for x to find what is the actual solution. What's the one x value that would work if we plugged into x for here and here. So now this is just a basic linear equation. Solving for x, we want to first subtract 4 from both sides. Okay. That gives us a negative 3x equals positive 3. Then we want to divide by negative 3 on both sides. And we find that x equals negative 1 is our solution. Okay. But before we can accept that as our solution, we have to make sure, is that part of our domain? Okay. So okay, is negative 1 part of our domain? So looking back at the top, our original expression, what x values can we not have? What x values are we not allowed to take in this problem? Well, here, we can't have x equals 0, because that would put a 0 in that denominator. So that's still fine. Negative 1 isn't 0. And over here, this fraction tells us 2 times x cannot equal 0. Well, that would again tell us that x can't be 0 here, because that would make that denominator 0. So the only value not in our domain would be 0. So x equals negative 1 is fine. It's part of our domain. Therefore, it checks, and it is our solution. And that's the one x value that would work. So going back to check to make sure you solve the problem correctly, 2 over negative 1 would give you a negative 2. And if you subtracted 3/2 from that, you should end up getting the same thing if you did 7 over 2 times negative 1. Yeah, this would give you a negative 7/2 if you plug in a negative 1 for x here on the right-hand side. And if you did 2 over negative 1, which would give you negative 2 minus 3/2, it will give you negative 7/2 as well. Okay? So you can go back to make sure it actually works, but you definitely have to go back to make sure that it's part of the domain. Okay, so even if you're going to be lazy about checking if the solution works, you don't want to be lazy about going back and seeing if it's part of the domain, because oftentimes you'll get an answer and then even though it's correct work all the way through, it's not part of the domain and you have to disregard it. Alright. Let's look at some more examples on the next pages of 7.4 notes. Alright, so continuing the same idea, we have an equation involving fractions, the rational expression. So we will want to find our lowest common denominator and then multiply by that on both sides of the equation. In other words, multiplying every fraction by that LCD. Alright, so we have x plus 1, that's one single factor. X minus 1 can be considered its own single factor because we couldn't factor those. However, we can factor the x squared minus 1 in order to see what two factors make up the x squared minus 1. So it is a difference of squares, so it's going to factor into a double parenthesis with an x and an x to get us that x squared, and then it would have to be a positive 1 and a negative 1 to get us that negative 1. And because they're opposite terms, opposite signs, the middle x term would cancel out. That's why it would equal x squared minus 1. So now coming up with our lowest common denominator, our LCD. Well, this fraction had an x plus 1 denominator, this had an x minus 1, and this fraction had an x plus 1 and an x minus 1, had both of them. So putting them all together, it's just our LCD will be the x plus 1, x minus 1. Alright, so that's what we're going to multiply by in each case. So what I always like to do is rewrite the original problem and just leaving space to multiply, all these. So I can do it here, 1 over x minus 1, leave some space to multiply by our LCD, so minus 2 over, it is x squared minus 1, but we already know it's factored, so, sorry, x plus 1, x minus 1, probably makes it easier to keep it in the factored form. So now we need to go through and multiply by the LCD in each case. So if x plus 1, x minus 1 times that fraction, x plus 1, x minus 1 times that fraction, and x plus 1, x minus 1 times that fraction. Okay. And once again, we can just look diagonally to see what factor is going to cancel out with our denominators. So diagonally here, again, you can think of this as over 1. So diagonally, we can cancel out the x plus 1 factor. And this fraction, the x minus 1 and the x minus 1, those are going to cancel. And then in our last fraction, the x plus 1 and x minus 1 is common to both. Think of this as over 1. So those are going to cancel completely. So since all the denominators cancel, once again, we won't have fractions anymore. This one's a little trickier though, because we will have some things we have to distribute. Here we have an x minus 1 times 3, so we are going to have to distribute that 3 into the parenthesis. Here we have a 1 times that parenthesis, so technically we aren't going to have to distribute, since multiplying by 1 doesn't change anything. I'm just writing it like that for now. And then minus 2, well, there's nothing to multiply the 2 by because those x plus 1, x minus 1 factors canceled out. So that just stays with minus 2. Alright, I guess going through and distributing 3 times x minus 1 gives us 3x minus 3 equals, distributing the 1 isn't going to change anything there, so just x plus 1 minus 2. And now you want to solve for x. Okay, all we are left with are single x's. Neither of these are x squared, so it's just a basic linear equation we can solve by getting our x terms on the same side and finding out what that one x value could be. So we could add 3 and subtract x, probably the first thing you'd want to do. Well, actually it doesn't really matter. Could add 3 and add 3 over on this side. So that's going to cancel out, but then over here we can do 1 minus 2 is negative 1 plus the 3 would give us a positive 2. So we'd end up having 3x equals x plus 2. I would then subtract the x to get the x terms on the same side. Okay, that would take us over here. Subtracting an x is going to give us 2x on the left hand side, and now all we're left with is that 2 on the right hand side. Divide on both sides by 2, and we get that x equals 1 is our solution. Okay, so before we can go ahead and say that that's our answer, we have to check and see if that's part of our domain. Can we plug 1 into our original fractions in all 3 fractions and not get a 0? If we put in a 1 here, we'd get 1 plus 1 is 2, that's fine. But if we put a 1 in here, 1 minus 1 would give us 0. So therefore 1 is not part of the domain. Okay, so we have to address that. That would be our solution, but 1 is not in the domain. Okay, so therefore the conclusion we make is that there is no solution. No solution, so there's nothing we can do on that one. If there was a solution, it would have been x equals 1, but in this case, none. Alright, let's try doing that, maybe one more time with this next example. Okay. So we have z over z plus 2 plus 6 over z plus 5. And then we have equals negative 18 over z squared plus 7z plus 10. You're going to have to factor that third fraction in order to see what factors make it up. So we can do that right now. Okay, factor this. And since it's a z squared out front, we know it's going to factor into a z and a z. Multiply to get 10, add to get 7. Well, that's going to be a 5 and a 2. You see those factors are going to be the same as these two factors. Doesn't always work out that way, but oftentimes in these kind of problems it does. So you kind of want to look for that. Look at these factors and assume, and check. You want to kind of hope that it matches these factors. So coming up with our LCD isn't too bad. It's just going to be combining those factors together. Okay, we have a 7 plus 2 factor, a 7 plus 5 factor, a z plus 2 and a z plus 5 factor. And then the last fraction has them both, so the LCD is going to be having both of them. Alright, so we want to write our original problem, z over z plus 2 plus 6 over z plus 5, leaving space to multiply by our LCD here and here, and then equals, we are going to have negative 18 over, keep it in the factored form to make it easy to see what's going to cancel out. So now we have to go through and multiply by our LCD. Z plus 5, z plus 2. Okay. And now we see what cancels out. So in our first fraction, z over the z plus 2 terms, here and here, cancel out. Second fraction, the z plus 5s will cancel out, leaving that z plus 2. And in our third fraction, the entire denominator is going to cancel out, leaving that negative 18. So this will give us a z plus 5 times z. Over here we have a 6 times that z plus 2. And in the last fraction, everything canceled, so we just have that negative 18 left. Okay. So we will have to continue by distributing and seeing what's left after we distribute. Distributing the z here, we get z squared plus 5z, plus distributing the 6, we get 6z plus 2, and it equals plus 12, and it equals negative 18. Okay, so we want to go ahead now and combine our like terms on the left hand side, seeing what we get. Z squared plus 5z plus 6z, that's going to give us z squared plus 11z plus 12 equals negative 18. And now in this problem, because we have a z squared term in it, and the z squared term isn't going to cancel out with anything, we have to solve this a different way. The z squared is going to require us to factor to solve. If they were single z's, we could just get them on the same side, combine, but as a z squared, it changes this problem up. So we want to get this problem, set it equal to 0, and factor. Okay. And specifically, why do we have to do this? Because the z squared term. Because it won't cancel out. Alright, so getting this set equal to 0, we'd want to get rid of this 18, so we have to add 18 to cancel out the negative 18. That's going to give us z squared plus 11z. 18 plus 12 gives us 2030. Okay. Now we need to factor the left side of the equation. This will require us to find two numbers that multiply to give us 30, but add to give us 11. Those two numbers are going to be, well, we're going to have a z and a z to get that z squared, and then 5 and 6 are the two factors we want to use. Multiplying 6 times 5 gives us 30, adding 5 plus 6 gives us 11. So those are the two numbers we want, equals 0. And now we check, or now we kind of use that zero product property. What z value would make this parenthesis equal 0? That's going to be negative 5. What z value is going to make this parenthesis equal 0? That'd be a negative 6. So our two potential solutions are either that z equals negative 5 or z equals negative 6. So those, again, are potential solutions. We have to check by seeing if they're part of the domain. So looking back at our original problem, I guess you can go all the way back to the top before we changed anything. Negative 5, can we have that in our denominators? Well, negative 5 plus 2, that will give us a negative 3 here. That's okay. But a negative 5 here would give us a 0. So we can't have that. That also would give us the 0 over here. So negative 5 we can't conclude since it's not part of our domain. But negative 6, if we look at there, negative 6 won't give us a 0 here or here. So negative 6 is a value we're okay with. So we want to write that the negative 5 is not part of the domain. Okay. Because negative 5 will make what expression? The 6 over z plus 5 part. It will make that be 0 in the denominator. Okay, so just kind of reviewing that idea and getting it down in words. Therefore, we say our solution is just the value z equals negative 6. So in that one, even though we found two potential solutions, we only take the one. All right. And then we have one more problem on the back. Here that is. We have 2x plus 1 over 3x minus 3 equals 6x minus 4 over 9x minus 24. So we can actually use the same method that we've been. We want to look at our denominators and come up with the lowest common denominator to multiply on both sides. But in this instance, our denominators aren't factored, so we're going to want to start by factoring our denominators. Okay. So doing that, we can come up with a both of these terms are divisible by 3, 9 and 24 are. So this is going to equal 3 parentheses 3x minus 8. Okay. And the other denominator, both terms also are factorable by 3. So if we pull out a 3, we'd be left with a x minus 1. Okay, because distributing back, 3 times x is 3x, 3 times negative 1 is negative 3. Alright, so from here, determining our LCD, a little trickier than on the last two problems, because it doesn't match identically with one of the denominators. Actually, I already kind of made a little mistake here. It's not just going to be double parenthesis. So the factors we have right now to consider. We have a 3 and x minus 1. Over here we have a 3 and a 3x minus 8. So combining all those different potential denominators, we have a factor of 3 we're going to need. They both have that. One of them had a factor of an x minus 1. The other one had that additional factor of a 3x minus 8. So there's our LCD. So we want to rewrite our problem and then multiply by that LCD. So our original problem, I guess right here, 2x plus 1 over the factored version, 3 parentheses x minus 1 equals 6x minus 4 over factored version, which is 3 times 3x minus 8. Now multiply here on both sides by our LCD, which is 3 parentheses x minus 1 parentheses 3x minus 8. Over here the same thing, 3 parentheses x minus 1 parentheses 3x minus 8. Okay. So now we want to cancel out any common factors diagonally. On the left hand side here we lose the 3's and we lose the x minus 1. Over here diagonally we lose the 3's and we lose the 3x minus 8's. So now whatever is left we need to multiply, or in this case distribute. So we have left is the 3x minus 8 times the 2x plus 1. Because it's two terms we do need to distribute. And over here we have 6x minus 4, so again two terms, and we need to multiply this by what's left, the x minus 1. Okay. So to clean this up, we'll need a FOIL. Okay. Foiling on the left hand side over here is going to give us 3x times 2x is going to give us 6x squared. 3x times 1, positive 3x. Negative 8 times 2x, negative 16x. And then negative 8 times a 1, minus 8. The right hand side, 6x times x gives us 6x squared. 6x times a negative 1, minus 6x. Negative 4 times x, a minus 4x. Negative 4 times negative 1, a positive 4. Alright, so now we do have x squareds, so it's looking like a problem we're going to have to factor. But in order to do that, you want to get everything on one side and get it set equal to 0. So in doing so, we could get our x squareds on the same side, so we want to subtract a 6x squared from here, and subtract a 6x squared from here. So then this gives us, well, the x squareds cancel out here, and they cancel out here, which is great, because then we don't have to, because then we don't have to deal with x squareds at all. We're not going to have to factor. So instead we just have the 3x minus 16x minus 8 equals negative 6x minus 4x plus 4. So we're not going to have the x squared terms. They'll cancel. We don't have to factor. Cancel. Which is good. Makes it a little bit easier problem to deal with. So now we can just combine like terms on both sides. 3x minus the 16x is going to give us a negative 13x. Drop down to minus 8. Negative 6x minus 4x is going to give us a negative 10x. Drop down to plus 4. Now we want to get our x terms on the same side and get our constants on the other side. So add 13x to both sides is one way to do it. Or you could have added 10x to both sides. Either way. Gets rid of those. Doesn't get rid of those. Adding there gives us 3x positive. We want to get rid of that 4, so we need to subtract 4 from both sides. Gives us a minus 12 over on the left-hand side and cancels out over here. So we get 3x equals negative 12. And then lastly, dividing by 3 on both sides, we get that x equals negative 4. Okay. And we do want to check that. Is that part of our domain? So going back up top, the x values we couldn't have up here looks like x equals 1 would not be part of our domain because it would make that become a 0. And then over here at this parenthesis, 3x minus 8, if we said what x value would make that 0, we'd add 8 to both sides and then divide by 3. 8 thirds is going to be the value there. That would give you 0. So in neither of those cases is negative 4 going to be a problem. So that's going to be our solution. So it's in the domain of our equation because it works for both fractions up top. Therefore, it's our solution. And that is it for section 7.4.